In this video, I'm going to be describing two special factoring patterns that we can use to help us save a few steps and a little bit of time whenever we need to factor and solve quadratics. If we can identify these two special types of quadratics, we can use their special factor patterns and factor and solve pretty quickly. The first special factor pattern is called a difference of squares. We're going to use this whenever we're missing our b term in our standard form quadratic. That's our first clue. And the second clue is that our first and last terms are being subtracted. That's the difference part in our name. We can't use this technique if there's addition. There is no such thing as the sum of squares. This is just a difference of squares factor pattern. So there's our second clue. The third clue is that you can take the square roots of your two terms. So if they're perfect squares and you can take the square roots, your roots are the things going in your binomial expressions. So the square root of a squared is a, the square root of b squared is b. We're just square rooting our two terms there. And those are our terms. One binomial set gets a minus in between them, and the other binomial set gets a plus. It doesn't matter which is which. Although for organizational purposes, if there are additional steps, it's always best to put the binomial with the minus sign first. So let's see if we can identify and use the special factoring pattern. So here we have a quadratic. It's missing its b term. We just have x squared and negative 9. Both of those terms are being subtracted, and they're both perfect squares. We can find the square roots of each of them. So the square root of x squared is x. The square root of 9 is 3. Those are the terms or numbers going in our binomials. One of our binomials is getting a minus in between them. The other is getting a plus. We can always check our factoring by foiling. So let's see why this special pattern works. If we FOIL, we got x times x, which is x squared, x times positive 3, which is positive 3x, negative 3 times x is negative 3x, and negative 3 times positive 3 is negative 9. Notice how our first and last terms are going to be all that's left when our middle terms, which always end up being opposites of each other with difference of squares, end up canceling each other. So positive 3x and negative 3x will cancel. And that's how we end up with only two terms, and we're missing our b term. Now, this special factoring method is not the only way to get to this factored form. We could have used our x factor technique that we learned a couple videos ago. Factors of negative 9 that add up to 0 are negative 3 and positive 3. So x factor method could still get us the factored form, but if you can recognize the difference of squares, then you save yourself a couple steps. Let's do another one where we actually factor and solve. So given this quadratic, another difference of squares, we're going to take the square roots of each of those two terms, write them in our two sets of binomials. So the square root of x squared is x, square root of 4 is 2. One set's going to get the minus in between them, the other gets the plus in between them. So there's our factored form. Let's take it one more step and solve or find the solutions, which are just the zeros of our factors here, or the opposites of the numbers that are in our binomials. So what would make negative 2, or what could I add to negative 2 to make it 0? Well, the opposite, positive 2. What could I add to positive 2 to make it 0? Well, negative 2. So our solutions are positive and negative 2. And actually, this is another pattern. The solutions of difference of squares quadratics are always going to be the positive and negative root of that last term. So another shortcut you can take to solve. Also, to solve this, we wouldn't necessarily need our factored form. We could use square roots in algebra. So if I add 4 to both sides and square root both sides, the square root of 4 is positive and negative 2. So again, not the only way to solve or factor. This is just a special way that we can do it. Sometimes difference of squares are not so obvious unless we divide out or factor out a greatest common factor. So looking at this quadratic, as it looks right now, it's not a difference of squares, but if we were to factor out a common factor of 2, or divide each of these terms by 2, then I would factor the 2 out, write it at the front, and inside some parentheses, I would write my leftovers after I factored or divided 2 out. So 2x squared divided by 2 is x squared. Negative 32 divided by 2 is negative 16. Again, we can check our work by distributing. So 2 times x squared is 2x squared. 2 times negative 16 is negative 32. So we can always verify as we're factoring that we're going along in the correct way. So now we have a difference of squares. X squared minus 16 is our difference of squares. We're going to use our pattern to factor that. That 2 stays at the front, still factored out, it's still hanging out. But now let's use our pattern. The roots of our two terms here are x and 4, and one of our binomials gets the minus, the other gets the plus. There's our factored form. If we wanted to solve it, we could just find zeros of our factored binomials here. So the 2 is actually not going to affect our solution. In fact, if we were to take it one step further to solve, we would divide both sides by 2, and that would get rid of our 2 anyways. So we're just looking for the zeros of our binomials, which are positive and negative 4, or in other words, positive and negative roots of that last term right there. Again, not the only way to factor and solve it. We could have used x factor. We could have also used square roots to solve. Add 32 to both sides, divide by 2, and square root both sides. We would end up with the same solution. There's also one more special case. It's called a double difference of squares. Sometimes a quadratic can be factored multiple times using the same pattern. So if we're looking at this quadratic, x to the 4th minus 16, x to the 4th is actually a perfect square, and the square root is x squared. The square root of 16 is 4. So those are the numbers or terms going in our binomials. One set gets a minus, the other gets a plus. And so here is why organizationally we put the binomial that is being subtracted first, because sometimes you want to always check and see, is that another difference of squares? And in this case it is. X squared minus 4 is a difference of squares, and we could use our factor pattern one more time to factor that binomial. So factoring x squared minus 4 gives us x minus 2 times x plus 2. X squared plus 4 didn't go away or disappear, it's still there, so we're still going to keep it there at the end. And then we can, so that's our factored form, but we can find zeros of our factors to solve. We're just going to focus on these two binomials first. So the zeros or the solutions here are just the opposites of what's in the binomial. So we got positive and negative 2. Those are what's known as real solutions. Because if I solve x squared plus 4 equals 0, I actually get imaginary solutions. If I subtract 4 from both sides and try and square root negative 4, square rooting a negative number gives me an imaginary, one or two imaginary solutions. And we're not going to include those. So at this level in math, we're not talking about our imaginary solutions yet. So I'm just going to focus on the two real solutions in this equation. So that's a difference of squares. Let's talk about the second special quadratic. It's called a perfect square, and there's a factor pattern that helps us take a shortcut if we can identify a perfect square. A perfect square can be created and used to solve a quadratic with a method called completing the square. That's an Algebra 2 level skill or beyond. I'm not going to focus on that yet, so we're just going to focus on identifying a perfect square and factoring it. To identify a perfect square, you're going to do one of two checks here. If your a term is 1, then all we have to do is verify that half the middle term squared is the same as the last term. However, if your a term is bigger than 1, you're going to have to do an extra little step there. You're going to take half the middle term squared and make sure it's the same as the a times c value. We're not going to see quadratics where that a term is bigger than 1 for perfect squares in this class, so we don't have to worry about that first check there. If we can identify it's a perfect square, we're going to be able to jump to the factored form in one step. So I'm actually going to pause this video and continue in a second part to finish off this pattern.